Welcome to this explainer. Today we're diving into something that literally feels like it was ripped straight out of a sci-fi novel, but it's actually happening every single day right in our own backyards. We are talking about true industrial process chemistry. We're going to explore how massive facilities take an invisible, completely deadly waste product and literally transform it into tangible, highly valuable elemental sulfur. It's just a brilliant feat of engineering, so let's jump right in.
So let's meet the two main characters of our story. First up, we've got hydrogen sulfide gas, or H2S. This is a highly toxic, corrosive, and heavily pollutant byproduct created when they process sour crude oil and natural gas. But, through some seriously clever chemistry, it becomes elemental sulfur, perfectly safe, bright yellow, and an incredibly valuable commodity that's absolutely essential to our modern world.
And that stark contrast brings up a pretty massive question, right? Oil refineries and natural gas plants produce relentless clouds of this toxic H2S gas every single day. If this gas was just vented into the atmosphere, we'd be looking at a total ecological disaster. We're talking severe air pollution and devastating acid rain. The stakes here are incredibly high. So how exactly do refineries stop this hazardous waste from destroying the environment?
Well, the answer is our technological savior, the Sulphur Recovery Unit, commonly known as an SRU, because strict environmental regulations rightfully demand that we protect our ecosystems. Refineries absolutely rely on the SRU to capture that hazardous gas and safely convert it. This isn't just some nice-to-have piece of equipment. It's a vital facility that ensures refineries comply with emission standards and keep our air clean.
At the very heart of the SRU is something called the modified clause process. Think of it as the core chemical engine driving the whole operation. It relies on a beautiful two-part chemistry. First, an intensely high-temperature thermal stage, which is then immediately followed up by a series of lower-temperature catalytic stages to finish the transformation.
Let's actually walk through this massive facility step by step. The journey of our toxic molecule travels through 5 major pieces of high-tech gear. It kicks off in the reaction furnace, flows straight into a waste heat boiler, moves through sulfur condensers, routes into catalytic reactors, and finally, the safe product drops into a sulfur pit. It is a highly controlled, tightly monitored journey from start to finish.
Stage 1. The thermal burn.
Inside the reaction furnace, it is a literal inferno. Temperatures soar between 1800 and 2400 degrees Fahrenheit. That's roughly 980 to 1315 degrees Celsius. To put that into perspective for you, that is hot enough to easily melt copper. In this extreme environment, the acid gas is injected, and using carefully controlled air, about 1/3 of that toxic H2S is intentionally burned right off. And here is exactly why that initial burn is so absolutely crucial. By torching just 1/3 of the H2S, we create sulfur dioxide, or SO2, along with some water. This is a very deliberate setup. We desperately need that SO2 for the catalytic stage. The furnace is basically prepping the perfect chemical ratio, so that the new SO2 can react with the remaining unburned H2S later on to create pure elemental sulfur. It's like a giant, perfectly balanced puzzle.
But wait, before we get to that second reaction, we've got to deal with those 2400-degree gases. Now, you might think all that intense heat is just wasted energy, right? No way. Modern engineering is way too clever for that. Those hot gases pass straight into a waste heat boiler. Here, the system recovers that extreme heat and actually uses it to generate valuable steam, which then powers other parts of the plant. It's just a fantastic example of industrial efficiency.
Stage 2. Catalytic conversion.
So what exactly is going on inside these clause catalytic reactors? Well, first, the remaining gases are carefully reheated to just the right temperature. Then, they're forced through specialized catalysts, typically made of materials like alumina or titanium. These catalysts act kind of like chemical matchmakers. They coax the remaining H2S and the SO2 we made earlier to react together, forming pure sulfur vapor. And to squeeze every drop of output out of this, it doesn't just happen once. The process repeats across 2 or 3 distinct stages.
Right after each of those catalytic stages, we have to get the sulfur out of its vapor form. The gases flow into sulfur condensers. And as the temperature drops, we see this dramatic physical phase shift. That completely invisible sulfur vapor cools down and condenses into heavy, liquid, yellow drops. This glowing yellow liquid flows safely out of the gas stream and collects down into a designated degassing and storage pit. Now, even after 2 or 3 passes through the catalytic reactors, there might still be a tiny, microscopic trace of unrecovered sulfur left in the gas. But regulations are incredibly strict, and the plant's commitment to clean air is relentless. Any leftover tail gas goes straight into a tail gas treating unit, or TGTU. Think of this as the absolute final net, catching those last trace amounts of sulfur compounds before any gas is ever released.
The final tally: waste into wealth.
Thanks to this incredible 1-2 punch of the modified clause process and the tail gas treating unit, refineries successfully recover a staggering 99% of the toxic sulfur from their raw materials. 99%. That is a phenomenal recovery rate, literally keeping millions of tons of pollutants out of our atmosphere every single year.
When you look at the sheer scale of this environmental triumph, almost the entirety of what's captured is just a solid, safe block of elemental sulfur, leaving trace emissions at an absolute bare minimum. The SRU is pretty much the definitive reason why modern refineries can actually operate responsibly and protect local ecosystems.
So what actually happens to all that recovered safe sulfur? It doesn't just sit in a pit somewhere. It goes straight out into the world to become vital, everyday products. It's a foundational ingredient for agricultural fertilizers that literally help feed the world. It's used to manufacture industrial sulfuric acid, rubber for the tires on your car, and it's even a critical component in advanced battery tech. We are literally driving, eating, and powering our lives using a byproduct that started out as a lethal hazard.
Honestly, understanding this permanently changes how you look at these massive industrial complexes. They are a brilliant example of industrial sustainability in action. Next time you drive past a refinery and see those towering structures, just remember, they aren't just processing oil and gas in there. They're actively executing massive-scale environmental protection and sulfur recovery.
We've seen how the modified clause process turns a deadly problem into an everyday solution. But it really leaves me wondering, what's next? What other dangerous invisible wastes are out there right now just waiting for a bit of clever chemistry and sustainable engineering to transform them into tomorrow's vital resources? Keep that in mind as you look at the industrial world around you. Thanks so much for joining me for this explainer, and keep staying curious.